Hi, everyone. My name is Michael Stewart. I'm a research fellow from the Centre for Transforming Maintenance through Data Science. And this is my presentation on our investigation into using large language models to perform failure mode classification. So failure mode classification is a task that is very often performed by reliability engineers. What it does is it aims to capture and code different failure and other undesirable events. So these codes are typically used for things like prioritizing improvement work and updating maintenance strategies. However, it's a very difficult task to perform manually, as all of the observations of each of the events are captured by field technicians in natural language. And I'll show you an example of what that looks like. So here we have a list of 5 different maintenance work orders. And you can see that each one of these captures some kind of failure. So pump runs for a while and trip, for example, could be considered an electrical failure. Engine does not work, might be considered a breakdown. Pump spraying out slurry, and the other 2 at the end, they would be considered potentially a leak. So recently, you may be aware, large language models have gained quite a lot of traction recently. There's a lot of interest in them, predominantly thanks to things like ChatGPT. So I'm not going to go into detail about how they work, but rest assured, large language models are massive models. They're deep learning-based models trained on massive corpora that encapsulate knowledge from many different domains. So essentially, we can think of them as being trained on the entire internet. So they've got lots of knowledge from various different domains, and we can kind of hypothesize that they will contain some maintenance knowledge as well, because of course there is maintenance information on the internet where these models were trained. So as a result of the scale of these models, they're able to perform many different tasks without doing any fine tuning. So we've seen things like writing essays, extracting entities. We've also seen ChatGPT, for example, being used to write code. So many different natural language tasks they excel at, really. So this is quite different from what we call regular language models, things like BERT, for example, which traditionally need to be fine-tuned or even trained from scratch on a manually annotated dataset to perform a specific task. For example, if you want to train BERT to do named entity recognition, you would need to provide it with some annotated data that humans have gone through and labeled, and then feed that into a model on top of BERT, for example, that then learns how to do named entity recognition. Whereas with large language models, you can actually get away sometimes without doing any fine-tuning at all. You don't need the annotated data. So large language models have been applied to several domains already. For example, we've seen examples in medicine, education, vehicle accidents, to name a few. And in our paper, we've kind of gone through some of these examples as well. So large language models, as I mentioned, they can be used off the shelf, meaning they don't need fine-tuning data. So when doing them off the shelf, you would require potentially something like prompt engineering, which is when you go and you structure the prompt to the language model in a particular way to try to elicit a specific response. Alternatively, you can fine-tune them. So you can give them annotated data, and this should help performance on domain-specific tasks, ones that they may not necessarily perform well at without doing fine-tuning. So the motivation of this work is that, to the best of our knowledge, large language models haven't yet been applied to maintenance, and let alone failure mode classification. So far, only text classification models, or regular language models, have been used so far. So the goal of this is to automate the process of failure mode classification using AI, because this represents a significant time saving for reliability engineers. I mentioned it takes a very long time for reliability engineers to go through humongous lists of work orders trying to classify the failures of each one. So automating that will save huge amounts of time and thus money. So it also allows for resulting failure mode codes to be aligned with existing classifications. For example, the ISO 14224 has a list of about 20 or so, potentially more, different failure modes. And this is good because quite often the technician who writes a work order will have a different idea of what the failure mode is from the reliability engineer who's interpreting it. So aligning them to those existing classifications allows them to be very consistent. So the aim of this work and this presentation really is to detail our investigation into using large language models to perform failure mode classification. And in particular, we're looking to answer 3 questions. Number 1 is, how should we engineer our prompt to make a large language model perform failure mode classification without doing any fine-tuning? i.e., we don't need any annotated data. We're just going to try to edit the prompt in such a way that when we feed it into the language model, we want to get consistent failure mode code for the particular observation that it's looking at. Secondly, we want to see whether it's necessary to fine-tune a large language model to perform failure mode classification. Do we actually need the annotated data to fine-tune? And finally, how do the large language models compare to traditional text classification models on this particular task? So to be able to answer these questions, firstly, we need an annotated dataset. So for this investigation, we're using a publicly available failure mode classification dataset. It's released as part of our paper, and you can see the link for the code and the dataset at the bottom of the slide. So this dataset contains approximately 500 observation label pairs for training, 62 for validation, and 62 for test. So the test records are the ones that we're going to be using to actually evaluate the scores of the models. And the training set we will use when fine-tuning the large language model and also to train the text classification model that we're using as our baseline. So the observations in this data set were extracted using named entity recognition. That's just taking a work order and extracting just the observation part of that. And I'll show you an example of the data in a second. And finally, the actual labels of the data were taken from a set of 22 different failure mode codes from the ISO 14224. So here's an example of what our data set looks like. So on the left, we've got the observations, and on the right, we've got the labels. So runs for a while and trip would be an electrical issue, does not work, could be considered a breakdown, and so on. So the goal of the model is to take an observation and predict a label. So for this investigation, we're going to be looking at 3 different models. The first one is GPT 3.5. This is just taking GPT 3.5 right off the shelf, not doing any fine tuning. We're just going to try to apply this to our data set and extract the failure mode codes. The second one is fine-tuned GPT 3.5. So we take GPT 3.5 and we actually fine-tune it on the 500 training records from our data set. And finally, FLAIR is the text-based classification model. So this is the model that we've previously shown to have the best performance on this particular data set. This is a, I guess, traditional text classification model, and it's been trained from scratch on the 500 training records. You can see the example in our paper at the link at the bottom. So question 1, how should we engineer our prompt to make a large language model perform failure mode classification without any fine-tuning? So the first thing we tried was just feeding a prompt into GPT 3.5 that says, determine the failure mode of the observation provided by the user. And then we just follow that prompt by the observation itself. So for example, runs for a while and trip. And this is what the model produced. So we've got 3 examples here. And you can see they're quite wordy, right? The label for the first one, for example, the failure mode of the observation, et cetera, suggests an electrical failure. It gives you this very long-winded explanation of what it is. And that kind of makes sense because GPT is, in essence, it's a chatbot. It's going to be kind of acting as if it, wants to be helpful, gives you a good explanation of things. However, for our purposes, this isn't particularly useful because all we're interested in really is just the failure mode code. We don't need all the extra text around it and everything. And in fact, this actually makes it more difficult to work with because if we wanted to get the failure mode code out of that, we would have to do further pre-processing. So clearly this isn't ideal for our purposes. So we need to work on the prompt a bit more. So realizing that this wasn't useful, we then add the following into the prompt. Your answer should only contain the failure mode and nothing else. So we're trying to kind of restrict the model to just give us the failure mode. We don't want anything else, no other text. This is like an example of prompt engineering. We're really trying to get the model to do something in particular. And now this is what we get after doing that. So now we can see run for a while and trip is overheating, which isn't necessarily correct, but at least it's just one label. Very stiff to operate, labels it as stiff operation. It's interesting to see what the model's provided here as the labels, because as far as we're aware, like, we don't know where these labels come from. It just kind of made them up, I guess. They don't seem to be aligned to any existing classification. And also, interestingly, even for example number 5, so high earth rating, it still produced some text, despite us telling it, please don't. So no failure mode can be determined from the given observation. And also, another interesting observation of this is that for some observations where the model wasn't able to produce a failure mode code, it gives you a different response every time. So has no equipment earth, it labeled as N/A and not applicable. And then for high earth rating, it gave us an explanation. So clearly these aren't consistent. It would be better if it just said NA for every single one it didn't know, for example. And then you can see the failed electrical one, it also added failure mode with a colon after it, which we don't want either. So clearly this is, I mean, it's better. We are getting some failure mode codes, but it's still a bit too wordy and not very consistent. So our final attempt at prompt engineering for just using this off-the-shelf model was to add a list of the valid failure mode codes from the ISO 14224. So we just add to the prompt, valid failure modes include, and then we just list the 22 of them, hoping that the model will kind of understand that we just want those ones. It shouldn't be trying to hallucinate its own ones, for example. But interestingly, after this, it still manages to hallucinate labels. So it comes up with interesting ones like failed to open, failed to adjust, can't be adjusted. We saw this quite a lot in the output. And it seems to be just kind of putting them together from different ones. So I think there's like failed to start on demand and, you know, things like that. And it's just kind of picking up pieces of different failure mode codes from ISO 14224, putting them together, and those are the outputs. It also seems to have issues with label consistency as well. So sometimes it would say fail to function, other times it would say failure to function. So clearly it's not very consistent, and it's kind of hallucinating its own labels, even though we've given it that list of 22. So the result of this first question is, it is possible to engineer the prompt to enable the large language model to predict failure mode codes, but they're not going to be aligned with existing classifications, and they are quite inconsistent. And this leads nicely into the next question, which is it necessary to fine-tune a large language model to perform failure mode classification? Or can we just get similar performance without fine-tuning, like using the prompt from the previous slide? So as I mentioned, GPT acts as a chatbot. So it's not going to respond with just a failure mode code unless we specifically ask it to or instruct it to. And before we can actually fine-tune our model, we need to kind of wrangle the CSV dataset into the correct format, which for GPT is kind of like a JSON file. I'll show an example of that in a minute. So to do this, we just wrote some Python code that kind of iterates over the CSV and converts it into the correct format to easily fine-tune GPT. And we've included our code for that at the bottom if you're interested. So you can use that to fine-tune your own model if you like. And this is kind of what the input to GPT will look like when you're fine-tuning. This is what our Python script produces. So you can see it's kind of arranged into 3 different parts. So this is one record from the training set. So for GPT, there's 3 different parts. There's the system role, the user role, and the assistant role. So in the system role, you're basically specifying what you want GPT to do. For example, for us, it would be determine the failure mode of the observation provided by the user. In the user role, you add what the user would say, or like the input basically. So for our case, it would be too hot. And then in the assistant role, you're specifying what the model is meant to produce given the user input. So for this example, it's overheating, because overheating is the failure mode for too hot. So we've essentially transformed the CSV into this and then used this data to fine-tune the model. And here are the results. So just interpreting this table. So on the left, we've got our failure mode codes, all 22 of them. Then we've got the column after that is the support. So the number of times that particular failure mode occurs in the test set, which was 62 records in total. Then after that, we've got our F1 scores of GPT 3.5, and then our F1 scores of GPT 3.5, but fine-tuned on those 502 training records. And if you look at the bottom scores, so micro and macro F1, you can see that the fine-tuned model is significantly better, like almost double the performance. It makes a massive difference to fine-tune it on those 500 records. And this is likely because of the fact that, as we saw, the non-fine-tuned model, it's still hallucinating kind of like failure mode codes that have been put together from various bits. So it can get some of them. Clearly, it's got 0.46 of them correct, but not 46% of them right. But it's, yeah, the fact that it comes up with its own random sort of interpretations of different ones significantly reduces the performance. Whereas the fine-tuned model basically doesn't do that from what we saw. It really sticks to those 22 that appear in the training set. And that results in it getting a very good F1 score of 0.81. And particularly on the sort of minority classes, the ones that don't appear very often in the data set, it does quite well as well. And just in general, like pretty much all the classes, fine-tuned does well. So the results of this second question are that fine-tuning does indeed have a significant performance on the F1 scores. So also just noting, we also tested few-shot learning. So this is where you provide a list of examples as part of the prompt. For example, in the prompt, you would include like, here's a few examples. So, you know, spraying that slurry would be a leak, engine doesn't work would be a breakdown, etc. We found that actually feeding those into the prompts didn't make any difference, at least for the fine-tuned model. We didn't see any performance improvements. And we believe that's because the 500 training records was sufficient in getting the model to understand the data. So ultimately, for question 2, fine-tuning is necessary to achieve a strong failure mode classification performance. You can do failure mode classification without fine-tuning, but you don't get very good scores, at least in our experience. You really need that annotated data to fine-tune it. Oops. So the final question is, how do large language models compare to traditional text classification models for failure mode classification? So to test this, I mentioned FLAIR earlier. This was our sort of baseline from a previous paper. So this is a state-of-the-art text classification model that has been trained on the training data set of 500 records. And these are the results of FLAIR compared to the other two. So it's the same table as the previous table that I showed you, but now we've got the FLAIR on the right with the scores. And you can see, if you look down the bottom right, FLAIR is kind of in between the two. It's in between the fine-tuned and the non-fine-tuned model. So FLAIR does better than not fine-tuning the large language model, but it's still quite a lot worse than the fine-tuned large language model. So ultimately, we can see that the fine-tuned large language model is better, like significantly better than the text classification model that's been trained from scratch on the same data. And what this means essentially is that the knowledge captured in the large language model is contributing pretty significantly to the scores. And especially, once again, the minority classes for the large language model are significantly better. So the classes that may not appear very often in the training set, we suspect that maybe the model has seen those somewhere in the data that it was trained on across the internet somewhere. And that kind of helps out with the minority classes a fair bit. So ultimately, the fine-tuned large language model is significantly better than FLAIR, but FLAIR is better than not fine-tuning at all. So what this really shows, these results demonstrate the importance of high-quality annotated data. Because even if you've got a large language model that's been trained across the whole internet, you still need annotated data, at least in this particular domain with maintenance, to be able to sort of outperform models that have been trained from scratch on annotated data. So I just included this slide as some other interesting findings of the investigation. So a few things here. So we noticed that the large language model, typically every time we run it, would provide slightly different outputs. And this is because they're not deterministic. So OpenAI provide a temperature parameter that you can set to 0, which aims to kind of minimize the differences between outputs, but it's still in our experience, it still kind of changes each time, which is problematic when you try to run experiments. So to combat this, we plan to do sort of cross-validation in our future paper, so that we can sort of solidify the results. Secondly, we noticed that OpenAI would sometimes refuse our requests entirely to fine-tune the model, which was interesting. So this is kind of different from how it used to be, I guess, when you fine-tune your model on your own computer. With OpenAI, you're using an API, other people are using it. Sometimes it gets overloaded and you just have to kind of wait a couple of hours, at least for us, because of server overload. Just something to keep in mind, I guess. And finally, we noticed, some people think it might be expensive to run, at least for us, with just 500 records in our fine-tuning set. We found that it was relatively inexpensive. It only cost $1 for each experiment. So that was good. So in conclusion, we've demonstrated the use of large language models to perform failure mode classification. And we found 3 things. So firstly, we can conduct prompt engineering to make a large language model perform failure mode classification without doing any fine-tuning and without needing any annotated data. But ultimately, the codes are inconsistent and the results aren't great. Like, it can be done, but it's not particularly good. I think the F1 score was like 0.46. It's fine, but not ideal. Fine-tuning on an annotated data set is really necessary to enable a large language model to exhibit strong failure mode classification performance. And finally, the large language models can perform better than a state-of-the-art text classification model, so FLAIR, on failure mode classification, but only when that large language model is fine-tuned on annotated data. And this really highlights the need still for high-quality annotated data. So future work for us. So we've submitted this paper to arXiv, which I'll provide a link on the next slide. We're planning to follow this up with a computer science paper. So this is kind of the work that's going to be put into that paper. So one of the key drawbacks of OpenAI is that all the data needs to be uploaded onto their servers to fine-tune the model. And for many sort of industry people, this presents a significant issue and basically makes OpenAI not viable. So as a result, we aim to investigate offline large language models, for example, Llama, because these can be run on a local server. There's no need to upload your data to anyone else. Secondly, we also aim to investigate how well FLAIR works when it is fed with GPT-based embeddings. So at the moment, I think we're using BERT embeddings, or sort of one of the sort of, not large language model embeddings, but just regular language model. It would be interesting to see how well FLAIR works if you feed it with GPT embeddings, because they should be better in theory. And finally, we plan to release a larger annotated data set. So you might have noticed the data that we're using is like relatively small, with only 62 records in the test set. It would be better to have a larger test set, just to get a better balance of different classes and that sort of thing. So we plan to annotate and then release a larger data set. And that's going to enable further fine-tuning. It would be interesting to see whether more data allows our models to perform better, and also improve the quality of the evaluation, as I mentioned. So that concludes my presentation. Thank you very much for listening. So I've included my email there in case you have any questions. I've also included a link to the paper I mentioned on arXiv that is essentially this presentation, and also the code for fine-tuning a model as well when running the experiments. Thanks very much.